Looking ahead now to week 9, we are dealing with estimates of population parameters. And so we're going to look at starting with population proportions here and how do we, different methods for estimating those population proportions. So the concept here is, again, we're going to be using samples because we've mentioned it's not possible or practical for us to look at the whole population and take data from that whole population. So we're using samples and those sample statistics to estimate population parameters. Now, the simple estimate is a point estimate. You just take a sample, you find the proportion of that sample. The sample proportion is signified by that p hat. The little hat over it tells us that's from a sample instead of the population. And then we just claim that that sample proportion should be close to the population proportion. And we showed in the last section last week that that sample proportion does trend towards the population proportion. It is distributed around that population proportion. Well, the next level, because that point estimate can still vary, it can be smaller or larger than the true population proportion. A little bit more reliable is a confidence interval, where we give an interval of numbers and we say, we're pretty sure that the population proportion is in this range of numbers. A little bit more reliable and a little bit more we can do with that as far as drawing conclusions about the population or claims about the population. And then we need to talk about sample size in a couple of regards. One is getting a sample large enough to have an accurate estimate. Too small of a sample, the smaller the sample, generally the worse the estimate is, or less reliable it is. And then if we want to make sure we have a certain level of accuracy, how big of a sample do we need to achieve that given level of accuracy, that to be within a certain margin of error of the true parameter? So the point estimate. The point estimate, as I said, is just taking a sample and finding the proportion of that sample, that p hat, and just saying that is the best estimate of the portion of the true population proportion, p. This is because, if you recall, in our sampling distributions from the last unit, if the population is approximately normally distributed, or if we have just a large enough sample size, proportions, by the way, are always normally distributed. The sampling distribution, in other words, the proportions of all the samples, form a normal distribution as well. The center of that normal distribution is the population proportion, p. And, of course, we have that sampling distribution gives us the standard error instead of a standard deviation to tell us how wide that distribution is. But as we said earlier, it is possible to have a sample proportion that's significantly smaller or significantly larger than the population proportion. So while the point estimate is going to give us an unbiased estimate of the population proportion, it is possible for it to be a ways off on either side. So here, if we use this to estimate the population proportion, it is an unbiased estimate. Like we said, it targets the population proportion. In other words, the population proportion is at the center of that bell curve, as we showed here. So as an example, if I have Sally Mae interviewing 950 undergraduate college students, 53% of them say that they take online courses. Based on this result, find the best point estimate of the proportion of all undergraduate college students who take online courses. Well, first of all, 950 is an adequate size. It's a decent sized sample. So we were pretty reliable there. And that sample proportion is an unbiased estimate of the population proportion. So the sample proportion of 0.53, remember 53% equates to a proportion of 0.53, is saying yes, we'd say about 53% of the whole population takes online courses. So a confidence interval is our next step. We showed that point estimate could be smaller or larger than the actual population proportion. So to account for that, we use an interval. We say, okay, we're pretty sure it's somewhere in this interval. Now, a lot of people mistake the meaning of this interval. They think, well, it's more likely to be at the center of the interval. It is not. The true population proportion is equally likely to be anywhere within the interval. So a confidence interval, again, we're looking at this bell curve. And we know the center of that bell curve is the true population proportion. Now, there's something called a level of confidence. And the level of confidence is usually given as a percent. A very typical level of confidence is 95%. So for example, let's use 95%. So then what we're looking at now is we want to find, we know the width of 95% of the data in the center of this distribution. Now there's 95% in that center. That implies that there's 5% outside of that, and it'll be split equally to 2.5% smaller than that interval, and 2.5% larger than that interval. Well, because we don't know the actual population proportion, we don't know where the center of this interval is. But we can estimate the standard error using either a known estimate of the population proportion or just a worst case scenario, which we'll look at later on in this section. We do have a decent idea of what this width is. And what we're going to do is from the center here out to this edge, that is referred to as the margin of error, the ME, or sometimes just E for error. And so we know what that size is, so we will use that margin of error to create an interval. Let's say my point estimate ends up being right here. Well, I take that margin of error and I go on both sides of that point estimate. Notice my true population proportion is in that interval. Or let's say my point estimate ends up being up here. Well, I go that margin of error on both sides of that point estimate. Again, my true population proportion is in there. What does the 95% level of confidence mean? Well, what it means is we go out far enough here for that margin of error that we would expect 95% of all sample proportions to fall in that range. So the 95% then is the margin of error big enough that we would expect that if we completed this process several times, or we took a sample, found the point estimate of the proportion from that sample, use that margin of error to create the interval, that 95% of those intervals are going to contain the true population proportion. So we're just going to say contain P, the population proportion. So let's look at this process more for how this is done. So first we talk about that confidence level, 95% or 0.95. What we're really using is going to be alpha. Alpha for 95%, which of course is going to be 0.95 as a proportion or a rate, as a rate. We do 1 minus the 0.95, gives us 0.05. This value is alpha. So alpha of a 0.05 is a 95% confidence interval. Alpha is the percent that is going to be outside of the interval. So here, if we have 90% confidence interval, alpha is 0.12, 95%, alpha is 0.05. That's the most common, by the way. 99%, alpha, of course, will be 0.01, 1 minus the 0.99. And as we saw in our example up above, whatever alpha is the amount that is outside the interval, half gets split to each end. So below the interval and above the interval, each have a probability of alpha over 2, or 1/2 of alpha. So one of the things we're going to be looking for is the z-score for those cutoffs. And that is called a Z of sub alpha over 2, which is going to be the critical value or the critical Z-score for that confidence interval. So if alpha is 0.05, alpha over 2 would be 0.05 over 2, which is 0.025. So what that means is, first of all, it's a 95% confidence interval of alpha 0.05. But that means that we're looking for here an upper tail. And we tend to look for the upper tail critical value rather than the lower tail, although the lower tail is just as easy to find, actually probably easier. Upper tail of alpha over 2 of the 0.025, which means, remember, Excel gives us the value that's below that. 1 minus that would be 0.975 is what we're going to look for to find our Z critical. If I go to Excel here, I want my inverse normal function. I'm just going to put in 0.975, mean of 0, standard deviation of 1. Now, if I leave out the mean of 0 and standard deviation of 1, by the way, Excel will assume that it's 0 and 1. It'll give me that. Oops, this is not going to allow me to do that. The newer version won't allow me to do that. We do have to enter the 0 and 1 so that it knows that we are discussing a standard normal distribution. Now, what if I had just done normal inverse of the 0.025? It's going to give me the same value, only negative, which makes sense. When we're talking about confidence intervals, because this curve is symmetrical, we are always going to have values that are the same value, just positive and negative. So this is a positive. Let's get back down here. 1.96 here. This cutoff down here would be a negative 1.96. Same values, just one positive, one negative. And yes, remember, we do use the 0.975 there, not 0.95. So this is just a visual summary of how we went about finding that. To get that critical value, or Z sub alpha over 2, of 1.96, and of course negative 1.96 on the other side. What that is saying is around the mean, or in this case, the population proportion, P, we have to go 1.96 standard errors to each side of that in order to reasonably expect to capture 95% of all those sample proportions. So here's just a summary of all those critical values. We could find each of those like 90%. So at 90%, alpha is 0.10. So alpha over 2 would be 0.05. So if I wanted to look that up in Excel. Now again, I'm just going to use the 0.05. It's going to give me the negative value, but I know that that's the same as the positive value. You get a negative 1.645 if I wanted to round that to 3 digits. Exactly what they're stating here, 1.645. For the 99%, well, alpha is 0.01, so alpha over 2 would be 0.005. So let's look that one up. So norm inverse, 0.005. It gives me the negative 2.57. This is saying negative 2.576. This is saying 2.575. Round off errors. I would say the 2.576 is probably slightly more accurate. So the way they found these values was to look in the table in the book. And what they looked for in that table is in the body of the table. So the 0.05, of course, is 95% or 0.95. The 0.05 is to the right. That means it's 0.95 to the left. And so what we're looking for in the table is a number as close as possible, 0.9500. And we trace it over and we see it's 1.6 here. And actually what we find is the 0.9500 would be exactly between 0.04 and 0.05 here. I believe that this ends up being .9495 under the 0.04 and .9505 under the 0.05. So we say it has to be between them. So 1.64, 1.65, we add them together and divide by 2 to get the average between those of the 1.645. And a similar thing happens for the 99. The 95% comes out to be almost exactly on. It's like 0.9, we're looking for 0.9750. We find 0.9751 or something like that in the table. So the margin of error, we mentioned this before. This textbook just uses E to denote margin of error. I've often used ME for margin of error. And this is taking that Z critical, and we're saying, okay, that's the number of standard errors that we move away from the center, from the point estimate to make our range, and we multiply it by the point estimate. So the margin of error, or just error, is that Z sub alpha over 2 times our standard error of our proportion. Remember the standard error of the proportion, I'll put it up top so we don't get our formulas crossed over, was the square root of P times Q over N. And so there's the formula, the margin of error, Z sub alpha over 2 times P sub P times Q over N. Notice it's a P hat because we don't have the population values. We'll use our sample values as our estimates. This is what's referred to as the walled confidence interval. If you're looking for an online calculator, you would look for walled, W-A-L-D, confidence interval. In Excel, we also have a walled confidence interval, but it is in an Excel stat add-on that we cannot add in here. At least I can't add it in because I don't have administrative rights to my computer, so I can't do it. But if you went to add-ins here and do the Excel stat add-in, it does have a walled confidence interval function in it. I'm not a big fan of it, so we'll look at some other calculations for it. So if we're going to find that margin of error by hand, we just go ahead and punch that calculation in. So we found that our critical value here was 1.96. Our estimate of P was 0.43. Q then, of course, would be 0.53 for P. Q would be 0.47, and our sample size was 950. If we calculate that out, I'm just going to do it on the on-screen calculator here. 1.96 times the square root of 0.53 times 0.47 divided by 950. Close my square root. I get 0.0317, and let's follow through and see how that comes out with our example here. So, must be careful to interpret confidence intervals, blah, blah. So we get the value here. Okay, so this is not actually looking at this example here. This is just an example of how we interpret the actual confidence interval. If we were to get this for a confidence interval of 0.405 to 0.455, the way we would say that is we are 95% confident that the interval from 0.405 to 0.455 actually does contain the true value of the population proportion. Notice what we did not say. One of the things we did not say there's a 95% chance that this contains the population proportion, because that's not true. Once we have remember, probability and chance only applies to future events. Once we have created the interval, either the true proportion is in it or it's not. There is no chance or probability involved there anymore. So saying there's a 95% chance that the true value of the proportion is between 0.405 and 0.55 is technically inaccurate. Another wrong way of saying it is 95% of sample proportions will fall between this, and that's not true as well. Remember, this is centered around The point estimate, the distribution of the sample proportions, is centered around the actual population proportion. So this saying that 95% of the sample proportions will fall between 0.405 and 0.455 would be assuming that the point estimate is equal to the population proportion. And remember, we said it's going to vary around it, so that's not quite correct as well. So remember, the correct way is to say we are 95% confident that the true population proportion is in this range. And so this is just kind of illustrating that if this is the true population proportion, we take our samples and we create those intervals, and we can see, in this case, there's one that doesn't contain it. The one in green, that interval does not contain the true population proportion. All the other intervals do. 95% of the intervals do contain that true population proportion. So let's actually construct that confidence interval now using the example we have before us. Some notation. P is the population proportion, I should say. P hat is the sample proportion. Small n or little n is the number of values in the sample, the size of the sample. E is going to be our margin of error, and z sub alpha over 2 is that critical value of z. Remember, that's the z-score that separates the interval in the center of our bell curve from the part that's outside of it. So first, we need to check to make sure our requirements are met here. This is a simple random sample. We're going to assume that those 950 former students that were surveyed were randomly selected. The conditions for the binomial distribution have to be satisfied. Yes, we decided ahead of time we're going to survey 950 people, and we did that. They're independent. One person taking online courses does not affect the probability of the next person taking online courses. And the probability that they're going to take online courses is constant from one person to the next. We didn't wait a year in between surveying people. And then we can reasonably expect at least 5 successes and 5 failures. Remember, this only really is important if we expect the proportion to be a really small number, like close to 0, or a really large number, close to 1. Here, we're expecting, our estimate is right around half. So out of 950, we're more than well satisfied the fact that we're probably going to have at least 5 successes and 5 failures. So let's find our margin of error in our example. Of course, this is our confidence interval. Once we find the margin of error, we take our point estimate and subtract it, and our point estimate and add it to get our ends of our interval. Round off rule, we're going to round our margin of error to 3 significant digits. That means after we hit our first digit that's not a 0, we go 3 digits from there. Again, this is just our procedure. We have to find our z critical, or z sub alpha over 2. We've already looked at that, and we calculate our margin of error using that formula. Once we have the margin of error, we take our point estimate, and we subtract the margin of error to get the lower limit of the confidence interval. And we take our point estimate and add the margin of error to get the upper limit of our confidence interval. Then we round to those 3 non-zero digits as specified. So back to the Sallie Mae survey here of 950 students. We had 53%. So N, the sample size, is 950. P hat is 0.53. If I want to find that margin of error for a 95% confidence interval, around our course, we're looking to estimate our population proportion. From that, can we safely conclude that more than 50% take online courses? We'll look at that question as we go on. And then as a reporter, briefly discuss what this means. So let's get to the calculation first. First, we need to check our requirements. We're going to assume that Sallie Mae made random samples here. The binomial distribution requirements are met. We had a fixed number of trials, 950 is our sample size. We didn't have any link between students, so having one student that took online classes does not change the probability that the next student will take online classes. And that probability of taking online classes was the same. We didn't wait a year in between or where classes might have increased or anything like that. And of course, with a 53% out of 950, we're pretty confident we're going to have at least 5 successes and 5 failures. Being that this is a confidence interval proportions, proportions are always approximately normally distributed, so we don't have to worry about that check. Our sample size is more than 30, so we're good there anyway. So let's find our confidence interval. First, we're going to find the margin of error. Now, I calculated that here on the calculator, found it to be, let's turn back on, 0.0317. They rounded it off to 0.032 as our margin of error. Then they used the point estimate of 0.53. They subtracted the 0.032 to get 0.498 is the lower limit of our estimate right there. They took the 0.53 and they added 0.032 to get 0.562, the upper limit of our estimate, so giving us that range. Now, this textbook always lists the confidence intervals like that. A lot of textbooks put it in interval form. They would write it like this, 0.498, comma, 0.562, in parentheses like that. That is an interval notation if you were getting into more of a college algebra course. Now, they mention XLStat. XLStat is the add-in I said for Excel. I don't have that on this computer, don't have administrative rights, so I can't add it. But we were able to pretty simply, once we found that using Excel to find our critical value, we were able to pretty easily then calculate that margin of error just on a simple calculator. Any scientific calculator will do that. Now, if you do have a graphing calculator, this is just a TI-83. It's an older version of the TI-84 that many of you might have from high school, or if you have kids in school. The TI-84 does a great job of this. What we would do is we go down to 1 proportion Z interval. So we got to go down a ways. These are tests up here. 1 proportion Z interval is option A here. This was in the stat. So let me clear back here. We pressed stat. We went over to the test menu. Now we went down to 1 proportion Z interval. Now X, we said 53%. We didn't give the number, so let's find that number. I'm just going to type it in here. Equals 950 times 0.53. Now, if this is a decimal, we do have to round it off. So they got 503.5. The calculator will not accept a decimal, so I'm going to put in 504 out of 950. Level of confidence is going to be 0.95 for 95%, and we'll hit calculate. There we get the 0.498 to 0.562. Little bit different, 0.499 to 0.562. Little bit different than what we had here, simply because of the round off I'm putting it in. But 0.498 to 0.562 is what we had here. Just a couple of extra decimal places after that in that calculation. So XLStat, you could do a 95% confidence interval for a proportion, the walled interval, and it'll spit that out. Again, I don't have XLStat capabilities on this computer. You really don't need them. It's simple enough just to type it in. And so the manual calculation, you could use the table. I prefer to use Excel to find my critical value rather than the table because the table is clunky. but you get that critical value of 1.96 for Z sub alpha over 2, and you plug in the numbers just as I showed before. You calculate as I showed on the calculator 0.0317382, and you take our point estimate of 0.53 or 53%. You subtract those to get the 0.498, then the point estimate plus that margin of error to get the upper limit of 0.562. So again, the proper way to state this is we are 95% confident that the true population proportion is in the range from 0.498 to 0.562. Or we could list it as percents like this if we would prefer. So then this is just restating that we're 95% confident that the true population proportion is in that range. Now back to that question we were asked. Can we safely say that more than half of students or more than 50% of students take online courses? And the answer is no, we cannot say that. We cannot safely conclude that. And the reason is because this interval here, so what we're saying is on the continuum, if this is 50% or 0.50, are we confident that the real proportion is somewhere up here above that? And we're not, because this interval dips down below 50% or 0.5. The interval that we created here starts below 0.5 and goes up. So it is very possible, since 0.5 is, or 50% is in that interval we created, it's very possible that the true population proportion is 50% or even slightly smaller. And remember we said even though it's at the very edge of this interval, the actual true population proportion is equally likely to be at any point in that interval. So we can't say, oh, it's at the edge, so we're pretty sure that it's more than 50%. No, we can't say that. 50% is in the interval, so we're not sure. It is very, very possible from this interval that 50% or less of students take online courses. So then the summary of the results, looking at this, we have a point estimate of 53% from this survey of 950 people. We came up with a margin of error of no more than 3.2 percentage points. That was that 0.0319 that we rounded to 0.032 in either direction of that point estimate by interviewing these undergraduates. So this is the proper way. This is the information you should always see if you're going to trust any sort of a survey that's presented on the news or online. First of all, what is their estimate? The 0.53 or 53%, they're estimating that 53% of undergraduates take online courses. But and of course, they're always going to say that part. They're always going to give you the statistic that they want you to believe. But they should also say sample size of 950 random, and hopefully it'll specify randomly selected. If not, that's a question you should always ask. And then, in theory, 95% of such polls we would expect to be within 3.2 percentage points of that result. If they don't say the 95%, and most often they do not say 95% confidence level, that's generally what you assume is it was a 95% confidence level in that survey or that poll. So when we analyze polls, again, should make sure it's a simple random sample, not some sort of inappropriate sample. Most of the samples you see presented for advertising or whatever are inappropriate samples. They're going to do whatever they can to try to get a sample that's in their favor. The confidence level should be provided, although it's most often not. Up here, we gave the 95%. If it's not given, usually you assume 95%, but you do have to be careful. If they don't give it, or if you ask about it and they don't give you that information, then I would seriously question how statistically accurate that study is. Most likely they're changing, they're altering the numbers a little bit to go in their favor. Also, they should provide a sample size. Many of them do not. Did they just survey 3 or 4 people, or did they do a large group? In this case, 950. That's for 2 reasons. One, to know, helps you say, analyze a little bit better whether it was an appropriate or inappropriate sample. But also remember that qualification of making sure we have reasonably expect at least 5 successes and 5 failures. If we have too small of a sample and we have a proportion that's either really small or really large, we have to worry about that. And then in rare cases, the quality of the poll results depend on the sampling method and the sample size. The size of the population is not a factor. So as long as they took a decent sample size, the size of the population really doesn't matter. In this case, 950 is more than an adequate sample size. So we don't need to know in most times we don't know anything about the real size of the population anyway. In fact, the only time the population size really becomes an issue is if the sample is too large. If the sample becomes more than 10% of the population, then we might have to make adjustments. So never think of a poll result being unreliable because the sample size is too small percentage-wise compared to the population. So percentage is the key word there. A small sample is a concern, but not small as in compared to the whole population. As long as it's a decent-sized sample, it does not matter how big the population was. Population size is not a factor in determining the reliability of survey results. And this is just our point estimate. If we know the interval, let's say I use the calculator here, and I got this confidence interval off the calculator, 0.48979 to 0.56226. Where is that? 49879, I should say. So 0.49879 to 0.56226. So if I have that actual interval like that, if I need to find what my point estimate was, well, I'm just going to add those two numbers together and divide by 2. 0.49879 plus 0.56226 divided by 2. Make sure that when you do this, you hit equals before you divide. So 0.49879 plus 0.56226. Hit equals and then divided by 2 to get the 0.53. Now this is saying a little bit off, 0.5305. 0.53 if we round it to 3 decimal places. And then to get our margin of error, we could, of course, just take this and subtract the lower limit, or take the upper limit and subtract that point estimate. Or we can just take the upper limit, 0.56226, minus the lower limit of 0.49879, and divide that difference by 2. So 0.56226 minus 0.49879. Hit equals again. Divided by 2, we get the point. Oops, I got a wrong number in there. 0.56226 minus 0.49879 equals, divided by 2, gives us 0.0317 or 0.032. So there are here's an example of where we're given a confidence interval. 95% confidence interval is from 58% to 81%. If I want to find the actual point estimate, I would add those together. 0.81 plus 0.58 divided by 2 is 0.695. So 69.5%. Here they said 70%, so that was accurate. They just rounded it. Then the margin of error, I subtract those. 0.81 minus 0.58 divided by 2, I get 0.115, so 11.5 plus or minus 11.5%. Works out with the numbers they gave in this example. So determining sample size. Many times we go into this surveys, and let's say we want to make sure we want our margin of error to be less than plus or minus 3% or less than plus or minus 2%, because we want to be able to state, hey, we're within 2% of the actual proportion here, or we're within 3%. To affect the margin of error, so we want a predetermined, we want to stay within a given value of E, that margin of error. The way we can do that is we can go lower confidence. Changing the level of confidence changes our critical value, so that could decrease the margin of error. We can't change our standard error because that's the proportion, and the proportion exists, so we can't alter that. So the only other thing we could alter is the sample size. A larger sample, a larger value of N means a smaller value of E. And so what we do is we take our margin of error formula and we solve it to figure C. So if we want to know how large of a sample N should be taken in order for the estimate to be within a given distance or a given margin of error for the proportion, we know that E equals Z critical, Z alpha over 2 times the square root of P times Q over N. Well, we're going to solve this formula for N to get that N equals Z sub alpha over 2 over our margin of error squared times P times Q. Using the same notation as we did for our confidence interval, there's our formula right there. Now they separated it out as Z sub alpha over 2 squared and the margin of error squared. I put the Z sub alpha over 2 over the margin of error and squared them after I divided it out. It's the same formula, just arranged slightly differently. If we know an estimate for P hat, we use it in this formula to find P hat and Q hat. If we do not have an estimate for P hat, we use P hat equals 0.5. Of course, if P hat equals 0.5, then Q hat would also equal 0.5. So that part that's P hat times Q hat would be 0.25. This is the worst case scenario. This is going to give us the largest possible required sample to get within that margin of error. So here's our example here. We want to get within a certain margin of error. The calculation for N that we get is going to be the smallest possible sample size. If we're rounding, we can't round down because the number we got is the smallest possible sample size. If we round down, that's going to be too small. So we always have to round up to the next larger number to guarantee that we have an adequate sample size. So even 708.13, even though it's only 708.1, it still rounds up to 709 because 708 would be too small. So in this calculation here, the survey of 4,787 randomly selected, now that's important, we're randomly selected, so we know that process is correct, shows 79% respondents do online shopping. If we wanted to conduct a new survey and we want that 95% confidence interval to have a margin of error no more than 3 percentage points, how big of a sample do we need to take? First, we're going to do it assuming that that point estimate from the first sample of 79% is accurate. Now, most times we haven't already done a sample, so we don't have that estimate. But here we did one sample already. We have an estimate. Before we do the next sample, we can use that estimate for calculating the sample size. So for 95% confidence interval, our alpha is 0.05, So alpha over 2, of course, is 0.025. And so we're doing that inverse. 0.025 would be on this tail. So we're doing that inverse of 0.975, giving us z sub alpha over 2 of 1.96. Our estimate of p is 0.79, so our estimate of q hat is 0.21. And so we plug those into the formula. 1.96 squared, remember that's the z sub alpha over 2 squared, times p hat of 0.79 times q hat of 0.21 over the 0.03 is because we wanted to be within 3 percentage points. That's a decimal of 0.03 from 3%. That, of course, is also squared. Calculating out to, as we mentioned earlier, 708.135, which will round up to 709. We need to have a sample of at least 709 adults to be relatively sure that we're within 3 percentage points of the actual value, that our margin of error is smaller than 3 percentage points. Now, what if we didn't do a prior survey and we didn't have that point estimate of 0.79 for P? Well, again, we use P hat of 0.5, which makes Q hat also 0.5. So when we multiply them together, P hat times Q hat is 0.25. Most textbooks still require you to put them in. This textbook just uses the shortcut of putting the 0.25 right in the formula. So again, we have our Z critical of 1.96. We're looking to stay under 3%. That formula comes out to 1,067.11, which rounds up to 1,068. So we need a sample of at least 1,068 adults to reasonably expect to be within 3% of our margin for our margin of error. So the interpretation here is at a 95% confidence interval. If we are looking to stay within a margin of error of less than 3 percentage points, if we don't have an estimate of the proportion, we need 1,068 people in our sample. If we do have that estimate, that 0.79 in this case, then we can reduce that sample down to 709 because we know that we're a little bit further from the center. So coverage probability, that 95% level of confidence, theoretically says that if we did this over and over again, 95% of those intervals would contain the true population proportion. The confidence interval for population proportion does not quite hold true to that. In the next section, we'll look at confidence intervals for population means. That holds very true to that percentage, that confidence level being the coverage probability. For proportions, it's slightly different. Now, there are ways of adjusting it. This was called a WALD or W-A-L-D confidence interval, and that's the only one we're going to use for this course. WALD was the statistician that developed this method. There's a +4 confidence interval. If you were to read on, there's mention of the +4 method. You add 2 to the successes and 2 to the failures. So you're basically increasing your sample size by 4. And for some reason, that makes the coverage percentage almost exactly equal to the level of confidence. For this course, we're not worried about getting that specific. There are several other types of confidence intervals. Again, we're not going to get into them. You can see here's one that calculates the margin of error with a very nasty formula. We're not going to get into those other methods, the Klopper-Pearson or the Wilson method. We're just using the WALD method, but be aware that there are other methods out there that actually are slightly more precise. This is a basic statistics course, so we're keeping it basic. We're going to ignore those other methods. Which method is best for this class? We are going to use the WALD confidence interval just because it is simple and it is close enough. And in most applications in the news, advertising and stuff, they are going to use a WALD confidence interval because, like I said, it is close enough. If you were to get into scientific analysis and actual research, statistical analysis, yes, they're probably going to use a more complex method. So with that is all for estimates of the population proportion. In the next session, we'll talk about estimates of the population mean.